Good day, everyone. We meet yet again on this wonderful day. Right, so we are still continuing on Newton's laws. The last time we tackled Newton's laws, we were busy with pulleys. We're still kind of going to continue with that, but today I just want to look at um, uh, instances where we are given a force that is acting at an angle. Okay, so let's get right into it. Now, please just remember to subscribe to the channel, and please, by all means, you are more than welcome to tell even more people. Just keep coming. And by the way, if you need to get in touch with me, my email address is mlungisi.m.nkosi@gmail.com. That's MLUNGISI dot M for Mary dot NKOSI@gmail.com. Should you have any questions, you're more than welcome to get in touch with me. All right, let's get into it. Now, so far we've been looking at instances where we've got forces that are horizontal and forces that are vertical. So today I want us to look at forces, what happens in an instance. So suppose we've got a body, right? A body of mass, let's say on some surface, okay? And we happen to be pulling that body at an angle, okay? So here's a force, and this force happens to be acting at an angle theta. Now, ladies and gents, please, I want you to note how would we tackle this? Right, now, the first thing that I want us to always look at or consider is that when you look at any situation, obviously we always start with a free body diagram. Now, let's assume that perhaps we've got frictional force here, right? So if we're to look at the free body diagram here, you've got something that looks like this, okay? So you've got force applied. So suppose we're pulling it at an angle, but it is moving horizontally. It's moving, in this case, in that direction, suppose to the right. Okay, so what forces do we have? Of course, we'll have the force that is applied at that angle there, okay? Right, which other force would we have? We know we'd have gravitational force. Remember, gravity is always pulling vertically downwards, right? Keep that in mind. So we say, well, this is the force of gravity or the weight of the object, right? So in this particular case, because we said it's moving to the right, we assume it's moving towards your right. So in this case, we're going to say, okay, we know friction opposes motion. So if it is moving, that's kinetic friction, right? So we know that kinetic friction opposes motion, right? Its motion is to the right, so friction should be in that direction, okay? So there's frictional force there, okay? So let's say F friction, okay? So this is force of gravity or the weight. And then we also have the normal force, okay? So there's our normal force there. All right, now, okay, nothing wrong with that system, okay? Please just make sure every time that you draw that your forces are actually attached to your central dot there. Remember, we said that dot actually shows us the center of gravity. Now, if you look at that drawing, right, we've got several forces. Remember what I said to you. We always add forces that are in the same dimension. So you never add forces that are in different dimensions, right? So what dimensions do we have here? So we've got the horizontal dimension. Okay, what are the forces in the horizontal dimension? Well, it's frictional force for now, right? And then you've got forces in the vertical dimension. What are those forces? We've got the normal force acting upwards, and we've got gravitational force acting downwards. So we can only add forces that are in the same dimension. Now, we've got a little bit of a problem here. You agree with me, ladies and gents? Right, we've got a force that is acting outside of those two dimensions, okay? If you want to look at it that way. So what do we do in that particular case, right, with this force? Now, ladies and gents, this is where I want you to please follow me and just listen carefully. So when we've got that situation, what we want to do is we want to resolve that force into components. Okay, so we want to get all our forces to be in the same dimension. Okay, we want to get, well, not in the same dimension, but want to get them into those dimensions that we spoke about, right? That is the horizontal as well as the vertical. So now let me try and redraw this free body diagram. Okay, now, okay, we said we've got the normal force here. If you don't mind, I'm not going to write the full words. I'm just going to represent that as N, right, so that it's a bit neater. We're going to have also the frictional force. So I'm going to just designate it as kinetic friction, right? And then we said we've got force of gravity, the weight, okay? So there's our W value there. Now, let's go back a little bit to something that we knew back in the days, right? We did that, I think, in grade 11, where we looked at forces in 2 dimensions. Now, when I look at that force, the force applied there, I realize that I can actually break it down into 2 components. It's got an equivalent in the horizontal direction. Okay, right, I'm going to call that Fx. All right, and then it's also got a component in the vertical dimension, so I'm going to call that Fy. Now, in terms of vectors, I know that Fx going that way plus Fy going that way gives me that force F there. Okay, so if you think about it, this force plus that force, you know, if you think about it as someone who was walking, if I walk in that direction plus that direction, well, it's the same as someone who just walked from there till there. It's what we call a resultant. Okay, so that kind of becomes the resultant force when I break it down in that sense. Now, so then I'm going to say, well, if this and that are the equivalent of that. Now, I can't have both of them, otherwise I'll be repeating myself, right? So, how about we replace that force applied there with its components? Okay, so instead of having that force applied there, let me rather have Fx and Fy. You can call it force applied X, force applied Y, whatever you want to call it. So let me have that force there. So there's my Fx value, right? There's my Fx. And remember, we had Fy going in that direction, right? Now, instead of having Fy here, remember I said every force must be actually attached to that center of gravity. So what I'm going to do is, instead of just drawing it there, I'm just going to put it there. I've changed nothing, I've changed nothing about my diagram. Okay, so I've got Fy, and I've got Fx. And remember, those 2 forces acting together give me that force applied there. It kind of becomes the resultant. So I've actually substituted those forces. Now, you may ask me, so how am I going to get that Fx and Fy value, right? Now, if you think about it, so back there, we had an angle of theta. So I had an angle here of theta, right? So if you think about it, Fx and Fy, this is horizontal and that is vertical. So what do I know? They actually make an angle of 90 degrees to one another. Okay, so then it means that I can actually take this as a triangle, a 90-degree triangle, isn't it? Right, now we're gonna go back to trigonometry, right? So I know force, this force, they called it F, right? And I want to find this side here. Now you remember there's a mnemonic that we use for trigonometry, right? We say, well, we've got what we call SOHCAHTOA. Okay, so what does that mean? It simply means the sine of the angle is equals to opposite over hypotenuse. Okay, the cos of the angle, all right, is adjacent over hypotenuse, all right, and the tangent of the angle is opposite over adjacent. So that's a little mnemonic that some of you may probably know now. Right, now look at this. I want to find fx. Now what does, which sides do I have here? Right, fy is opposite to our angle. Can you see that? So that's the opposite side. Remember, opposite just simply means directly in front of something, all right? So that's opposite, okay? So it's directly in front of our angle. So that's our opposite side, okay? And then you've got fx, right? Now, we say this is the adjacent side. Remember, adjacent is just a fancy word that just means next to, okay? So there are two sides that are next to the angle, right? It's this one and that one, but remember, this one here, we call it the hypotenuse, right? So we call this one the hypotenuse. That's the longest side to your 90-degree triangle, right? And then you've got this side here, and obviously we'll call that side the adjacent side. Now, I want you to please look at this. Okay, sorry that my drawing just looks a little bit cluttered there with all the words. But I want you to see. So fx is on the adjacent, okay? And remember, I'm given the force applied. They said it was F, right? So now, which trig ratio has adjacent and hypotenuse? Okay, can you see? Adjacent and hypotenuse. So that's going to be the cos, right? So I'm showing you where this comes from. So the cos of theta is actually equals to adjacent, the adjacent side. We said that's fx, okay? And divided by, that's the ratio, the hypotenuse. My hypotenuse is what? My hypotenuse is f. So that simply means if I wanted to find, now please, I want you to look at this. If I want to find the equivalent fx, all I simply do is say, well, if I cross multiply fx times 1, that's fx, and then that's equal to f multiplied by the cos of theta. All right? And please remember this, ladies and gents. Right, so I'm looking for that horizontal equivalent, right? So I'm looking for that horizontal equivalent of that force there. So that will become f the cos of theta, right? And then, what if I'm looking for that fy value? And you'll see just now, we're going to use those values. That's very, very important. So we're going to use those values. What if I'm looking for now for the value of fy? Let's go back to our drawing. Our drawing simply says this is our angle. So fy is the side that is opposite. It's opposite our angle, right? And remember, we are given this side here, and this side is f, right? So that's our hypotenuse. So which trig ratio says opposite over hypotenuse? So that's going to be the sine of theta. You're quite right. Okay, so that means, okay, that means the sine of theta, is equal to, now remember, that's fy, that's opposite, okay, as sine of theta opposite over hypotenuse. So that's opposite, which is our fy value, right, divided by the hypotenuse, which is f. So that means that if we wanted to find the value of fy, once again, we're going to do the very same thing. So fy is going to be, if we cross multiply f, the sine of theta. Now, in most cases, you are normally given that angle there, but should that change for some or other reason, I mean, say maybe they give you the angle here, just for argument's sake, right? you can always get the value of that angle, so that you can come back to this. How do you do that? Obviously, this if they give you, let's say, that angle there, this angle here will be 90 minus whatever the value is there. Okay, right. But nonetheless, all I'm simply saying, here's an angle. We're given an angle of elevation, right? Or even sometimes we're given an angle of depression. I've seen a situation, okay? Maybe we'll get one of the questions that use that concept. In fact, it's important so that I show you how to apply that. Right, so in this case, all you simply do, when you've got a force that's acting at an angle, all you simply do, break that force down into its components, right? So Fx, right, that horizontal component, that's F cos theta, and then that's the vertical component, that's F sine of theta. Now, ladies and gents, please, I want you to listen carefully. If you look at this drawing now, what have I done? I've got now only 2 dimensions. Can you see that? Right? So if I were to say, consider, all right, let's take the sum of forces in the vertical dimension. Okay, so if, let's say, this was an object that was moving, we know that F net would be equal to 0. Okay, right? Why? Because it is not moving vertically, right? Sorry, let's just start with F net is equals to MA. Let me rather start there. Right, so F net is equals to MA, right? So now, what does that mean? It means if I take the sum of forces in the vertical dimension, okay, that is going to give me a value of 0. Why? Because my acceleration, it's not accelerating rather in that dimension. So as a result, now look at this. I'm going to take, let's say, just upwards as positive for my vertical dimension, right? So it means that my normal force plus my Fy, okay, this is very, very important, ladies and gents. Right, normal force plus Fy, right, minus the weight, or minus the force of gravity. Why am I saying minus? Remember, because it's acting in the opposite direction. Right, so all of these are now equal to 0, okay, because it is at equilibrium in that dimension. Now, why am I showing you this? Because we might have instances where we are going to be actually calculating the frictional force, okay? So then it means if we're given the coefficient of friction, we'd have to now find the value, the normal force, and look at what the normal force would be now, right? Take everything to the other side, this becomes positive, so it's going to be weight minus that vertical equivalent of the force. Can you see? Right, so this becomes very important. Now, if you remember when we were calculating the gravity, what do they call this? The normal force previously, we only had 2 forces that were acting in the vertical dimension. It was the normal force and the weight. But now I want you to consider this. Now we've got another force there, which is Fy, and that's why our normal force would not be as it was before, right? So now it would be what? The difference between those two. So normal force plus Fy will be equal, minus W rather, the weight will be equal to 0, and therefore that would be the difference there. I hope that makes sense, ladies and gents. Okay, don't worry, in a few we're going to take some practical questions. Right, similarly, because it's moving in the horizontal dimension, okay, so we'd be able to get the frictional force from that. Okay, now because it's also in the vertical dimension, it's moving, so once again you'd be able to say F net is equals to MA, right? So now we are looking at the sum of forces in which dimension? In the x dimension, right? It's equal to mass times acceleration. Now, which forces are acting in the horizontal dimension? You're quite right. So in this case, let's take in the horizontal dimension, let's say that's a positive direction. So this would be equal to Fx minus the frictional force, and this would be equal to ma. Okay, so if you look at this, all right, so Fx minus the frictional force, Fx is in that direction, it's positive. We said going to the right is positive, then minus the frictional force, which will be equal to ma. And obviously we can do a calculation from that. Now, ladies and gents, let's try to remember what we've done. We said if we've got a force that's acting at an angle, the first thing that we're going to do is break that force down into its dimensions, into components, right? Okay, we take those components and what do? We find their trigonometric equivalents. We said, okay, we said cos theta over is equals to Fx over F, right? So Fx was equals to F, the cos of theta. All right, we did the same with Fy. It was opposite, so it's opposite over hypotenuse, which was Fy over F, right? And then Fy is F sine of theta. Okay, so please just remember that. All I simply did, took that force and broke it down into its equivalents. Okay, right. I hope I've been able to whet your appetite just now, okay, with all of this. So what I'm going to do in just a few is let's just take a practical question where we actually apply this principle. Is that okay? Good. All right, let's get to it. Right, so let's take that system there. So suppose we've got a force that is applied. Okay, you know what, let's say the value of that force, okay, let's just put a 100 newtons of force there. Okay, right, so we've got 100 Newton force that is applied to a trolley. Okay, so let's just say the trolley is accelerating in that direction, okay, with an unknown acceleration. So say the coefficient of friction, kinetic friction in this case, 0.35. So let's calculate the frictional force, right? Now, please, you'll forgive me, I've actually just try to make it as simplified as possible. We'll take past exam questions in just a little while that are more specific. Right, now, so what do we want to do? So the first thing is, okay, I think the one thing that the examiner always going to do is, first of all, ask you to state Newton's laws, right? Either one of the three laws, so you must know that. And then secondly, probably they might ask you to draw a free body diagram. So that's where I want us to start. We'll always start there, right? So let's do that. So free body diagram, what are the forces that are acting? Of course, we've got the force applied there. Okay, so we'll say that's force applied, that's force F. Okay, we've got gravitational force. Okay, there's our force of gravity or the weight. And then if you assume that it's accelerating in that direction, so definitely friction would be opposing the motion. So there's our frictional force value there. Okay, so that's friction, force of friction. And then also, because it's sitting on a surface, so this would be the normal force acting on it right there. Right, so this is what our free body diagram is. And I did say to you, ladies and gents, that depending on the number of forces that you have, you'll see that the mark allocation is always corresponds. It always corresponds rather to the number of forces that you have. Okay, so now let's try to calculate the frictional force. Now, the first thing is, we want to make sure that we take all the forces in the vertical dimension. But what do we realize? I'm sure you already see it. This guy is misbehaving, right? So what do? we're going to break that force down into its components, isn't it? Right, so we know that's 30 degrees there. So we're going to break that force down into its respective components in the horizontal, right? And then in the vertical. Can you see? So it's going to the left and it's going upwards. So in this case, let's do exactly that. So here's an equivalent of a diagram, okay? So it means that we'd have normal force there, you'd have friction, okay, you'd have gravitational force, right? And then instead of drawing that force, what I'm simply going to do is let me replace that force with its equivalence, right? So I'm going to have Fx in that direction, but remember, horizontal, and then I have the vertical. So I'm going to put Fy there, right? So that's Fy in the vertical dimension. But how did we say we calculate those two dimensions? Now, please note, I haven't done anything in answering the question, right? So if you want to, you know, it always helps. I always try to work in a systematic way, right? Let's just calculate Fx and Fy. If you remember, right, how did you get Fx? We said it's F, the cos of the angle, theta, that angle of elevation there, right? So get that angle of elevation, we said it's 30. So our F value is 100. So 100 cos of 30 degrees, all right? Let's see, what does that give us? So that's 100 cos 30, okay? So I get a value of 86.6, okay? So that's 86.6 newtons, okay? Look, if you want to, you may work within the force equation, okay, so that you try to minimize the rounding off whilst you're working at this. Particularly if you are an engineering student, you remember that you always work with significant figures, right? I'm not really going to be very pedantic on that for now. That's another story for another day. But you remember that you always work with significant figures, right? So, and I've got my Fy value. That's going to be F the sine of theta. Right, so that's going to be 100. The sine of 30 degrees. Remember, sine 30 is 0.5. So that gives us a value of 50 newtons. That's our Fy value. So these two equivalents, remember this and that put together, they give us that force applied there, okay? Right, now, okay, they said to me, calculate the value of frictional force. So let's answer the first question. How do I get the value of frictional force? So remember, to get frictional force when I'm given the coefficient, right? Remember, frictional force will always be equal to the coefficient of friction multiplied by the normal force, right? And what does this give me? Okay, the coefficient is 0.35, okay, multiplied by. Now, how do we get that normal force value? I'm glad that you remember. We said, okay, but I look at my vertical dimension. Do you see that I've resolved all my forces now into horizontal and vertical, right? So the normal force plus Fy, right, minus the force of gravity would be equal to, so I'm going to do this just on the side here. So it means that the normal force, right, plus Fy minus the force of gravity. Remember, what are those equal to? So I'm taking the sum of my forces in the vertical dimension. And I know the sum of those forces would be equal to 0, right? So in this case, normal force plus Fy minus Fg, this is equal to 0. So my normal force, right? I want the normal force to substitute it there, right? So my normal force would be Fg, if I take it to the other side, minus that Fy value. Now, how do I get the force of gravity? Right, you remember we say mass times gravitational acceleration, isn't it? Right, our mass is 12, okay? Our gravitational acceleration is 9.8 minus our Fy value is 50, right? Okay, yeah, hope you can see it well there. Okay, so I'm going to do that. Remember, we found our Fy value here, so this is 12 times 9.8 minus 50, and I get 67. So my normal force is 67.6 newtons, right? Okay, so now I'm going to substitute that normal force there, so that's 67.6 newtons. Okay, multiply that by 0.35 and we get 23.66 newtons. Okay, now ladies and gents, nothing wrong if you wanted to do all of this within that equation. I'm just so I want to make it simpler for you by actually working it out separately. Okay, I hope you can still get that. All right, so now let's go to our second question. So in our second question, they want us to now calculate the acceleration. All right, so we're assuming, or rather they told us that this thing is accelerating in that direction, right? So I'm going to take direction to the left, okay, as positive. So I always consider direction of motion as positive, right? Especially this is going to be extremely helpful when you do work energy and power as well, right? So so we know that F net is equal to MA. Keep that in mind, right? So now what do we know about our F net value, right? So we are taking sum of forces in the horizontal direction to be equal to MA. And so remember, Fx, you are quite right. So that's the horizontal equivalent of our force. So that's Fx minus the frictional force, and this is equal to MA. Right, we've already calculated our Fx value, right? So that's 86.6. If you wanted to, you could substitute it as is, 100 cos 30, right? Minus the frictional force. Remember frictional force value, we found that 23.66 value is equal to our mass is 12, and we want to find the acceleration, right? So how do we get that acceleration? You know, all that's left is for us to do our mathematical gymnastics, right? So that's 86.6 minus 23.66. Okay, and we divide that all by 12. Okay, right, I get an acceleration value of 5.2, okay, let's say 0.25 meters per second squared. I've just so we find that it's accelerating in that direction. How do I know? Because my acceleration came out positive, so it must mean that it's accelerating to the left. Okay, right. I hope that makes sense, ladies and gents. Right. So you see why it was important for us to break it down into dimensions, so that because it will affect. Now, I've seen one solution in the past where the examiner who gave that memo actually forgot about this Fy value. Please just remember, once we've got a force that's acting at an angle, that tends to affect our normal force, the calculation for the normal force, particularly if you're going to need it. Okay. Right, so there it is, right? I'm glad that you are getting it, okay? Right, so I want us to move on to a past exam question, obviously. And they're going to give us more than this, okay? So I'm going to show you how we apply this. Nothing changes. All we simply do is just follow the same approach. Right, so let's take this question here. Took it from the March April 2020 paper for the senior certificate examination. Just gonna zoom into it just a little bit there, okay, so that you can see it better. All right, so they said two boxes, P and Q, resting on a rough horizontal surface, are connected by light inextensible string. Now, those of you who've watched my previous videos, remember I said the fact that it's light, it simply means that its mass is negligible. It won't add to the mass of the entire system. Okay, and then inextensible just simply means whatever happens to the one should happen to the other. Okay, so it's not a you know, like a rubber band or something like that. Okay, so they say the boxes of mass 5 kgs and 2 kg respectively. Okay, a constant force F. Okay, so there's that force F at an angle. Acting at an angle of 30 degrees to the horizontal is applied to the 5 kg box as shown, right? They say the two boxes move to the right at a constant speed of 2 meters per second. Now, you can see the examiner tried to highlight something very important for you, right? The moment they tell us about that constant speed, then we remember, what does that have to do with? Now, please, ladies and gents, so the common error is that once you see this number, you just assume it's the acceleration. Constant speed, what does it tell us? It simply tells us that acceleration is 0, right? Remember, acceleration is 0. It takes us back to Newton's first law, right? So once it moves at constant speed, it means that we've got an acceleration of 0. Now, okay, they say state Newton's first law of motion in words, right? You remember that first law, right? It says a body will remain at rest or in constant motion in a straight line unless it is acted upon by an unbalanced set of forces. Okay, all right. Now, of course, some of you may want to say that differently, but nonetheless, we all get to the same place. Right, now, so what I want us to do, let's tackle that question together, right? Okay, I'm just going to put it this side, okay, where it's going to be visible to you. Right, so now they say draw a labeled free body diagram for box Q. Okay, so box Q is this one here, right? So what are the forces that are acting? Now remember, we're pulling this at an angle there, right? So the boxes are able to move. So in this case, they told us it's a rough surface here. So what does this do? So the tension on the string here causes this box to start moving also to the right at 2 meters per second. So now if we're going to draw a force diagram, okay, so let me draw it here. So what do we have? We've got the tension on the string. Okay, so there's our tension value. If you don't mind, I'm just gonna zoom out a little bit so that I have a bit more space, right? So I've got the tension there, okay, and then so there's my tension T, and remember they said labeled, so that means that either you write out the words in full, or please remember, if you don't write out the words in full, what you simply do is you are going to write out the symbols here and then just write T, tension on the string. Okay, right, so and then what do I have? That's force of gravity. Okay, so that's tension there. Okay, and I've got my normal force. That's the normal force. And then obviously because it's a rough surface, that simply means we have frictional force, F, friction. Okay, right, so there it is. Okay, alternatively, as I said to you, you could have chosen to rather take those forces, okay, and just try to yeah, so just try to rather write the symbols. That's what I was trying to say. Write the symbols and then just write the words in full. So force of gravity, force of friction, you know, and so on. Okay, right. Now the next question, they say to us, okay, so I'm just gonna zoom in once again so that you can see that, okay, a bit more clearly. Okay, so they say box P experiences a constant frictional force of 5 newtons, right? And box Q a constant frictional force of 3 newtons. So meaning both the boxes are experiencing values of frictional force. Now please note, this is not the friction coefficient, but it is the frictional force. Can you see that? No? Right, so how do we deal with those forces there? Now they say to us, calculate the magnitude of F. Okay, right. Now that we have drawn the free body diagram, now that's out of 5 marks, isn't it? Okay, so now that we've drawn the free body diagram, oh, sorry, that's out of 6 marks. Oh, right. So now that we've drawn the free body diagram for this guy, now they said calculate force F. Okay, that means we're dealing with that force there. Right, now let's look at it. This is now, I'm going to go for the 5 kilogram object. Now remember, this we're answering 2.2, right? So for the 5 kilogram mass, okay, I'm not answering the question just yet. Let me deal with the forces first. What are the forces acting? It's going to be that force F acting at an angle. It's going to be the normal force, right? Please allow me to do that. So that's force F, that's the normal force, that's gravitational force, okay, as well as the frictional force. Oh yeah, something I forgot to mention. So can you see, you're given 4 marks there, so that simply means that the expected 4 forces, and that's exactly what you have there. Okay, right, now let's deal with force F. Okay, I'm trying to show you nothing has changed. Okay, right, now remember we said, nah man, we need to actually resolve this into its components, isn't it? Right, and you still remember, how do we get the components? So here's the drawing with components. So that's normal force, that's friction, okay, that's Fx, that's going to be Fy going upwards, all right, because this and that give us that. So this going that direction and that going in that direction. So those are the 2 forces, right? They give us that back. And then we also have the force of gravity. So that's Fg, right? So what do we do? So we're looking for force F. Now, I won't deal with the vertical dimension. You know why I won't do that, okay? The reason why I won't deal with the vertical dimension is that normally we deal with that when we want to find out the frictional force. But I am given the frictional force in this particular one, right? So let's rather work with the horizontal. Is that fine? Right, so I'm going to say, okay, so F net is equal to MA, right? Remember, we're still on the 5 kg, right? So the sum of forces in my horizontal direction or dimension is equal to MA. So what are those forces? It's going to be Fx, okay, right? I'm going to consider direction to the right as positive because the motion is to the right. So that's Fx minus our frictional force, so that's Fk, right, which is equal to MA. Right, now please, I want you to remember, what did we say? We said this thing is moving at a constant speed of 2 meters per second. So what's our acceleration value? So acceleration value should be 0. So now I want you to look at this. How do we get our fx value? This is going to be f the cos of 30. You remember that from our previous example, right? Said, all right, we're looking for a horizontal equivalent. It's the cos, it's adjacent over hypotenuse. So that's f cos of 30. Our hypotenuse is f. So that's f cos 30 minus the frictional force. Now, what's our frictional force value? Right? They said for block P, the constant frictional force of 5 newtons. So friction is 5, okay? And that gives us what? That gives us, oh no. Ooh, I seem to have forgotten something. Sorry about that. Ladies and gents, I almost made a very, very serious error. Now look at this. I forgot to actually include the tension there. Okay, right. Now if you look at this diagram here, I've got force applied. Okay, so there's my force applied, normal force. I had frictional gravitational force acting downwards. I had frictional force, but remember, I also have the tension on the string here, right? So please make sure that it's also in the same direction, right? So I have the tension on this string. So that means that I also have the force, the tension on the string. Okay, so there's my tension there. I included it in that diagram, but I didn't do that in this one here. Okay, now please, I've seen some of you draw tension. You know, that's why I said to you, it's actually important that you try and draw a big dot instead, so that you can accommodate multiple forces that are going in the same direction. Okay, right. Now please just forgive me for what I've done here. Okay, yeah, even the best of us make mistakes, right? So I want you to look at it. So we've got fx, right, minus the frictional force. Okay, so I was supposed to say minus the tension. So let me just remove this here, minus the tension, and this is equal to ma. Is that okay with everyone? Right, so friction, fx minus friction, it's in the opposite direction, minus tension, right? And this is equal to ma. Now look at this. We've got now f cos of theta, that's this fx value, minus 5, right? That's our frictional force, minus the tension, okay? Right? And this is equal to what? Remember, our acceleration is 0, so therefore that gives us a value of 0. Now, ladies and gents, I hope you can see this. Okay, so now we end up having a scenario where we've got two unknowns. Can you see? Right. So because I use that, I've got two unknowns, right? So I've got f cos theta minus 5 minus tension. I do not know what f is, but I also don't know what the tension is. So if you don't mind, let me call this equation 1. Okay, right, I'm going to leave it there. If you wanted to, you are more than welcome, by the way, to even go as far as saying f cos theta, f cos 30 rather, minus 5 is equal to, right, if you take that to the other side, that becomes a positive. So that's equal to the tension, and you can have that as your equation 1. Nothing wrong with that. Okay. Now, where are we going to get our equation 2? Our equation 2 is going to come from the fact that, now, I'm trying to actually move this thing here. Right. Now, remember, this was the drawing for what? For just the 5 kg. And this was the drawing for the 3 kg, right? Sorry, for the 2 kg block. So this one here, right? So now I'm going to also take the sum of forces in the horizontal. So I'm going to say, all right, now we are dealing for the 2 kg block, okay? Right, we also know that F net will be equals to what? 0, because it's actually acting in the, because it is moving at constant speed. Okay, so it's moving at a constant speed as well. So that means what forces are acting there? That's tension. Remember, I took right as positive, minus the frictional force. Okay. Okay, so let me call it friction 2. Let me call this friction 1. Okay, or if you want to, you can say friction P, because that was block P, and let's call this friction on Q. Okay, right, and this is equal to 0. Now the tension minus, what's the frictional force that acts on block Q? They said constant friction of 3 newtons, right? So in this case, we're simply going to say minus the 3 newtons. This is equals to 0. I'm sure you can already see this. So the tension value is equal to 3 newtons. So now you can take this value and substitute it there, right? In equation 1. So that means that F cos 30 minus 5, okay, is equal to 3. That's our equation 1. We are substituting for that tension. Right, so F cos 30 is equal to, if I take that to the other side, plus 5, right? So that's 3 plus 5, which will give us 8. And we can divide both sides by the cos of 30, right? Alrighty. Okay, so we've got 8 divided by the cos of 30. And that gives us a value of F to be 9.24 newtons. Okay, right. I hope you can, you are still with me, despite the error that I almost made here. Sorry about that terrible writing over there. So that's Fx minus friction minus the tension. Okay, sorry about that terrible writing over there. Okay, right. I hope everyone is okay. All right, still with me. And then we got the value of F to be that 9.24 value. Right, now let's move on to the next question. So we've got ourselves some 6 marks there. Okay, right. Now, someone else actually, might as well just maybe address this for someone who chooses the other option. Someone else could have actually taken this as an entire system, right? In which case, they would have actually considered it as though the force F is acting on the entire thing. Now, remember that the string or the tension on the string is actually an internal force on the system, right? If I'm going to take this as an entire thing. So you could have actually just simply said F net, right, is equal to MA. Now, please, I want you to note this. I'm taking this as an entire system. So it means that it would have been Fx, right, minus, now, what is the frictional force that's acting on the whole thing? That's going to be 8 newtons because it's going to be the 5 here and the 3 there. So that's minus the frictional force is equal to 0. So remember, so as a result, this now would have been Fx. This is F cos of 30 minus the friction, okay, which is 8, right, the sum of the two, and this would be equal to 0. You see, you'd be back to that again, and so you'd get that value to be 9.24 newtons. Now, the reason why I actually chose to take that whole long method is because I'm trying to be as consistent as possible. That's what I showed you in our previous videos, right? So I'm trying to be as consistent as possible in terms of breaking that thing down into its components, okay, or into different parts, okay, right? So you would still be able to get that there. Right, now let's go to the next questions. Okay, let me try to fit it over there. Okay, right, so now they say the strings connecting rather P and Q suddenly breaks after 3 seconds while force F is still being applied. So just imagine when the string breaks here. Now think about it. what would happen when the string breaks? Okay, right. So now it means force F would be pulling only the 5 kg block, right? So it means it's pulling a lesser mass. It was pulling 7, but now it's going to be pulling 5. What's going to happen there? Remember what Newton's second law said. He said, well, the acceleration is directly proportional to the net force, but it's inversely proportional to the mass. What does that mean? The smaller the mass, the greater the acceleration, right? Now think about it. If I'm looking at that there, it means the 5 kg block would start moving faster than it did before, right? So as a result, the force F stays the same. Now it's pulling a lesser mass, so in this case, it would actually start accelerating, moving faster. But what would happen to the 2 kg block, right? Remember, the string has been cut off, right? So in this case, what would happen if the string breaks, right? What would suddenly happen to this guy? If this was a if it was a frictionless surface, it would still continue at 2 meters per second. However, it's not. It's a rough surface, so it means that it would actually now start slowing down because friction would be the only force acting on it. So as a result, it would actually slow down. They usually refer to that as deceleration. But let's just say it's slowing down, right? So now they give you a diagram there. Okay, so these were the two blocks moving together, right? Their velocity was constant at 2 meters per second, but at that 3-second mark there, you can see one of them starts increasing in velocity, another one starts decreasing, just like I explained to you. So X would be increasing in velocity. So which one would that be? Okay, that should be the 5 kg block, right? And then Y would decrease, so that would be for the 2 kg block. And then they want you to write down the time at which the string breaks. Of course, it breaks at 3 seconds. I'm not sure why they asked that question, because they already told us it's at 3 seconds. Okay, and then they say which portion X, Y, or Z of the graph represents the motion of block Q, right? This one here. Okay, so that would be this Y portion here. They say use the information on the graph to fully support the answer. So what I would say there is that, first of all, remember we're going to use Newton's second law, right, to answer that. So we would say, okay, when the string breaks, okay, right, so when the string breaks, the acceleration, or rather the net force that acts on the block Q, right? So the net force acting on block Q, okay, is the frictional force, which opposes the motion, isn't it? Okay, so what does that tell us? That the acceleration of block Q would be in the direction of the net force, and so that's why it would accelerate in the opposite direction. So remember that deceleration is actually seen as acceleration in the opposite direction, or you can say that's why it will actually slow down. Okay, right. I hope that was helpful, right? Trying to show you that we don't always just draw calculate acceleration, right? So I want us to take another question that's kind of the same, or rather that involves situations where we've got forces that are acting at an angle. Okay, right, good. I hope you were super duper with this. Let's move on to the other question. Right, so I'm gonna do this question last, okay, as our last question. So we're given, this is from the November 2020 question paper, by the way. So they say to us, so a 20 kg block resting on a rough horizontal surface is connected to block P and Q by a light inextensible string, there's that thing again, over a frictionless pulley. Okay, so they say block P and Q are glued together. Okay, so we've got blocks P and Q that are glued together and have a combined mass of M. So both of them have got a mass M. Right, now they say to us a force of 35 newtons. Please, you're going to have to be very careful here. A force of 35 newtons is now applied to the 20 kg block, right? So there it is there, at an angle of 40 degrees with the horizontal as shown. So at an angle of 40 degrees. Right, now what is happening to the system? We need to find that out. Okay, right, and then they say to us the 20 kilogram block experiences a frictional force of 5 newtons, of magnitude 5 newtons, right? So sitting on that table there, okay, as it moves to the right. Now please, I want you to be careful here, at a constant speed, right? So they are telling us this entire system, or rather the block, the 20 kg block, is actually moving to the right. Can you see? Now, this is just trying to say to you, ladies and gents, you must always be mindful of what the instruction of the examiner is, right? Now look at this. We've got an entire system now. We've got a force that is applied in, in that direction, but the system is moving to the right. Ooh, okay, right. So it means that force is not enough, okay, to overcome the pulling of the gravitational force there. Okay, so despite us applying a force in that direction, still gravity is still greater in that case in terms of its pulling force, right? I hope that makes sense, right? Okay, right. Now the first thing that they say to us is define the term normal force. Remember, we said the normal force, it's a force, or the component of a force which the surface exerts on an object with which it is in contact with, and which is perpendicular to the surface, right? That's a formal definition. So we know that it's a force, or a component of a force, okay, which the force exerts, which is with which it is in contact with, okay, and that which is perpendicular to the surface. Okay, so that's our normal force value. Okay, right, now moving right along swiftly. Okay, so we are looking at certain things there. They say draw a labeled free body diagram of the 20 kg block. Now, ladies and gents, I want you to please stay with me on this one, right? So I'm just going to zoom out a little bit, okay, so that it can accommodate us in terms of space. So I'm going to look at forces that are acting on the 20 kg block, okay? So there's our mass there. We have the applied force. So that's force applied there. Okay, we are labeling our forces. So that's force applied. And then we know we've got gravitational force there. Okay, so that's our force of gravity. Okay, we also have, sorry man for my terrible drawing. We've got the normal force. All right, okay. Now please, I want you to note this. We also have tension, which is pulling this guy. Now remember, they told us that this entire system is actually okay, rather they said this one is moving to the right. So what does that mean for this one? It means for P and Q, they're actually moving downwards, right? So then there's a tension on the string that causes a tension there, remember we said if we've got a frictionless pulley, the tension on the one side must be equal to the one on the other side. So that means that we've got a tension force there. Okay, that's caused by the string. Okay, so we've got the tension there. And then we also have, look at this now. Okay, so we have frictional force. They told us it's experiencing a friction of 5 newtons. Now I want you to please remember, we said friction is a force that has a tendency to oppose motion, isn't it? Or rather, that opposes motion in this case, because they did say it's moving. Okay, so it's moving in that direction. So friction has to be acting in that direction there. So I'm going to say this is the force of friction. Okay, or you can say that's kinetic friction. All right, now that's the diagram that we have. Now, you know, with many people, they always think that, look, friction must oppose the applied force. Please just be careful about that. Friction only opposes motion, right? So in this particular case, we're applying a force there, but in this case, where is the motion? The motion is in that direction. So as a result, friction opposes that motion. So as I said to you, this was out of 5 marks. Guess how many forces we have, right? That's 5. Okay, so now they say to us, calculate the combined mass M of the 2 blocks. All right, so we wanted to find this mass here. Okay, right, so let's try and look at what we do there. So now for the 2.2 value, right? So in this case, what are we going to do? We're going to simply say, okay, so if we look at, let's say block P and Q, né? So if we look at block P and Q, okay, so that was 2.2. So if we look at block P and Q, so they're experiencing a force in that direction. So it means that we've got force of gravity in that direction, right, which is pulling this guy downwards. And we've got also the tension that is actually pulling up in that direction there. Sorry, maybe I should make this slightly longer. So, and remember, our system is at equilibrium, right? So as a result, what do we know? We know that F net, okay, is equal to MA. Okay, so so we said F net is equals to MA. So remember that we are going, we're taking this as it's moving downwards. So that means that the force of gravity minus the tension, right? Remember, we said that it's moving at a constant speed, so that simply tells us that this is 0. The acceleration is 0. So look at this. We've got 9.8, the force of gravity. That's 9.8 multiplied by the mass, and our mass is M, right? Minus the tension, okay, right? And we don't know what that tension value is, okay? And that's equal to 0. Okay, now if you notice, in this particular case, we have a little bit of an issue because we've got 2 unknowns. Okay, so if you wanted to, we can just simply say, well, it means that the tension, right, if I take that to the other side, is equals to 9.8 M, right? And you can just designate this as equation 1. Okay, so now where are we going to get our equation 2? Obviously from that. And I'm going to only take some of forces that are in the horizontal dimension, right? So I'm going to say, well, once this is now for 20 kg, okay, so for 20 kilograms, I'm going to say it means that F net is equal to MA. But once again, what do we have? We've got tension, right, minus the frictional force. Okay, if you've been following in what I'm doing, right? So now, what are we going to do with that force applied? Of course, we're going to break that down into its horizontal and vertical equivalent. So in a sense, we've got that normal force, we've got that tension, which is in that direction, we've got friction, which is in that direction, we've got Fx, goodness, we've got Fx, which is in that direction, okay, and then we also have Fy, okay, so that Fx and Fy, simply substitute that guy, and then we also have the gravitational force. Okay, so now I'm only looking at forces in the horizontal, so that's going to be tension minus friction minus that Fx value. So that's tension minus friction minus that Fx value, and all of this should be equal to 0. Okay, so we said our tension value is 9.8 m. Our friction value was given as 5, and our Fx value, we always said that's F, the cos, so that's going to be 35 cos of 40, and this is equal to 0. Okay, all that's left for us to do now, ladies and gents, is just to simply work out. Let's see what we get there. I'm going to have those two values, so that's going to be, if I take them to the other side, of course they become positive, so that's 5 plus 35, the cos of 40, okay, and we divide that by 9.8. Please, you can do this on your own, ladies and gents, and that simply means that I get a mass of 3.25 kilograms. Okay, right, so you can take this as in its entirety as a system. Okay, if you wanted to take it as an entire system, for those of you that have asked me about that, okay, so that means I would have said 9.8, so you would have had to add those two masses. In fact, let me just avoid that because that will make a huge mess. Okay, right, and then lastly, they say, how will each of the following be affected when this, so they had a statement before that. They say at a certain stage of motion, block Q breaks off, so it's the same thing that happened in the past example. Block Q breaks off and falls down, so block Q. So it means that that mass is actually now less than what it was before, right? So they're asking what will happen to the tension. Okay, so in this case, remember that the tension depended on the mass there. So in this particular case, of course, it means that the tension would definitely decrease. And then they say what will happen to the velocity of the 20 kg block. Okay, and you must explain your answer. Of course, if I decrease that tension there, it means now the resultant force decreases, right? Remember, the resultant force is the sum of forces in that horizontal direction. So that would decrease. So as a result, it means that your they had said choose increase, decrease, or remain the same. So I would have, of course, would have chosen decrease. And in this case, just the explanation of the velocity there. So if the tension decreases, right? So that simply means the resultant force would decrease, and therefore the acceleration, it means that the acceleration would decrease. Okay, or in this case, because resultant force has decreased, okay, it means that the system will now begin to decelerate, or you can say accelerate in the opposite direction. Okay, right. Now, ladies and gents, I think I want to leave it here. Remember that you can still do the same thing. You can subscribe, you can tell people about this channel. Okay, and I hope next time we'll be able to look at systems whereby the force, okay, where we are dealing with the force that is acting on an inclined plane. Okay, but for now, please just make sure that you follow the channel, that you subscribe, and that you continue working on physics. All right, thank you so much. Sharp, sharp.